Prediction and validation of the transverse mechanical behavior of unidirectional composite considering interfacial debonding through convolutional neural networks. Outlines: Introduction, Numerical Modeling and Simulation, Convolutional Neural Network, Results and Discussion, Conclusion. To predict the mechanical behavior of unidirectional UD composite, many researchers conducted random RVE models and conducted FE simulation. However, this method also requires high computational cost because of the material properties have to be judged in terms of mean and standard deviation of the simulation result of many RVEs. The support vector machine and logistic regression were used to classify the material phase. Artificial neural networks were employed to predict the material properties of the unknown input after training the relationship between input and output dataset. The purpose of the present work is to provide a simple and powerful data-driven model for predicting the transverse mechanical behavior of UD composites. The CNN model was used with the input dataset consisting of microconstructor images and output dataset containing FS-curve obtained from a transverse tensor simulation of RVE of UD composite. The accuracy of the proposed model was confirmed by comparing the prediction result of several test datasets having random fiber positions with those of transverse tensor simulation. It is noted that the accurate prediction of the mechanical behavior was made within only a few seconds of the test dataset with the proposed CNN model, learned by training dataset. S-curve was predicted that includes entire material response without the principal component analysis. Numerical modeling and simulation. The corresponding FE simulation of RVEs consisting of fiber and matrix were generated by using Abaqus Python script. For each VF of 40%, 50% and 60%, 300 samples were constructed, resulting a total of 900 samples as shown in figure. From the result, it was found that the three statistical spatial metrics for generated RVEs of 60% very close to CSR pattern. To simulate the transverse mechanical behavior of a decomposite of T300 and 7901 was assumed. The metrics of each constituent are listed in Table 1. In an actual transverse tensor test of UD composite materials, a debonding phenomenon occurs where the fibers and matrix are separated, which affect the transverse mechanical behavior. To capture the phenomenon, the interface zone between the fiber and matrix was modeled using a cohesive zone model following the traction separation law. In order to perform this modeling effectively, an in-house code was developed so that the interfacial layer could be arranged according to the along the edge of the fiber. A transverse tensor simulation was then conducted by imposing the periodic bounding condition of the RVE with Abaqus standard. All the transverse tensor simulation result of SS curve with generated RVEs are plotted in figure 4. To check the validation of FE simulation, a comparative study was conducted with test result of UD composite of VF 60%. In case of transverse elastic modulus, FE simulation value and of value is similar to the result obtained for the test. As Vf increased, E22 increased, and Ut slightly decreased due to increased stress concentration fiber. The deviation of SS curve after passing the peak of SS curve increased because of debonding between the fiber and matrix started, which causes highly nonlinear material behavior according to the various fiber arrangement of each RVE. In the same time, elements in the cohesive zone started to be damaged at the peak and finally were debonded, with an increase of applied strength. Here the red region indicates the debonding areas. Convolutional neural network. Binarization of microconstructural images. In this work, we developed a prediction model using CNN Toolkit in MATLAB Deep Learning Toolbox. All of the RVEs used in transfer tensor simulation were converted to binary images as input dataset as shown in figure. The fiber were white pixels and the matrix and interface were black pixels. The resulting image has total of 64 million pixels of 800 by 800 images. The employed CNN model consists of one input layer, one output layer, one or more convolutional layer, and pooling layer and a fully connected layer. 900 images in total were inserted into input layer and filtered through a convolutional layer to extract appropriate features. Corresponding SS curves that were divided into 40 even stress and strain points for each SS curve were used as input datasets for training the CNN model. The convolutional layer using 3 by 3 filter, a feature map that emphasizes the area of image, is output by using convolution of weights defined in the image and transmitted to the next layer with value as a activation function. The result of convolution layer can be transmitted to the next intact by downsampling. The pooling includes max pooling using 2 by 2 filter displays the maximum value in the specified Carnot window size. A fully connected layer is represented as a one-dimensional array with trainable weights and biases by connecting all the nodes of the previous layer and the nodes of the next layer in the same way as general neural network. In other words, the repetition of the convolutional layer and pooling layer includes local features in the image and also expresses global features and transmits them as input to the fully connected layer, and the fully connected layer outputs the final result. Ny and y bar denotes the number of dataset, FO simulation, and Sreystrand value of CNN prediction. The overbar means the average of the variable. To assess the performance of developed CNN model, the mean squared error, mean absolute error, correlation coefficient and relative percentage error of toughness were calculated. As shown in figure, CNN prediction result of two images with 400 pixel and 400 pixel and 800 pixel by 800 pixel is shown, which is almost identical, which means the 800 by 800 in this work are sufficiently accurate. In this figure there are 9 RV samples that were randomly chosen with the predicted S-curve by proposed CNN model, which are compared with S-curve obtained through FE simulation results. Here the red dot lines are S-curves of CNN model and blue dot lines are S-curve of corresponded FE simulation. Here is the result for uh, sample 2. Here we can see that the lines of FE simulation and CNN prediction almost overlaps, and the first one is the result of 40% VF, and second one is the result we get when we use the 5 composite with 50% VF, and the third one is the result we get when we use the composite with 60% volume fraction. Here is the result for sample 3. So we can see that in 3 cases, the composite with 60% volume fraction gives the most accurate result. For mean value of MSE, MAE, and relative percentage error of toughness, the 800 by 800 pixel images with 900 RV samples showed better correlation results than the other cases. In addition, the results indicated the CNN model with input and output dataset could produce better correlation while offering sufficient accuracy. An adequate correlation is noted for the 9 test dataset between the FE simulation result and CNN prediction result within the relative percentage error of toughness less than 2%. Despite the complex nonlinear behavior of S-curve, the CNN prediction results are very close to the elastic part and UT of the S-curve. To improve accuracy, it might need more input samples and properly trained data augmentation. In this work, a simple, powerful data-driven CNN model was developed to predict the transverse mechanical behavior of UT composite. It is seen that the trained CNN model accurately predicts S-curves of UT composite, showing the nonlinear behavior caused by interface debonding beyond the elastic limit of unknown test data images. It is concluded that the model can easily generalize the relationship between microconstructor and material properties of UD composite materials with the SS curve encompassing the entire material response. This approach can be extended to more non-circular arbitrary fiber shapes of UD composite and has potential application to actual microconstructor image and 3D CT images. RSA is a new method where we can uh, use to generate random distribution of fiber. Convolutional neural network, it is a type of artificial network where you use the image recognition and processing that is specifically designed to process pixel data. Max pooling is a operation that selects the maximum element from a region of the feature map covered by the filter. Thus, the output after max pooling layer would be a feature map containing the most prominent feature of the previous feature map. ReLU is the max function with input "x". Metrics from a convoluted image. ReLU then sets all the negative values of the matrix "x" to 0 and all the values are kept constant. ReLU is computed after the convolution and it is nonlinear excavation function like sigmoid.